So welcome back, everybody, and I hope you had a great break. Recharge your batteries. And I should say welcome to the last topic, general topic this semester, which is about generative methods. And we are going to start with a class of methods which are called energy models, and they are also known as Boltzmann machines. And these were actually introduced back in '85, roughly, by Hinton, who got the Nobel Prize in Physics. And it's very much inspired by methods from statistical physics and statistics. And I always like to start with the Boltzmann machines or the energy models, because that allows us to make a kind of way to introduce many of the concepts without going into some of the difficulties which we encounter with variational autoencoders and the diffusion models. But the basic ideas are laid out when we start looking at the Boltzmann machines. So we are going to look at a class of these machines, which are called restricted Boltzmann machines. And today we're also going to remind you of some of the basic elements of statistics, some basic theorems like the product rule, marginal probabilities, conditional probabilities, and Bayes' theorem, which we will encounter again when we look at variational autoencoders, diffusion models, etc. Now, when we do this, there is an important element, which without that would not have made these calculations possible. And that important element is called Markov chain Monte Carlo. So that is the way we're actually going to generate expectation values. And you will see that one of the tricks which we end up having to deal with is to calculate the expectation value of the log of the probability when we calculate gradients. That leads, when you have mentioned something like Markov chain Monte Carlo, or MC squared, as we normally call it, then we need to have a rule for accepting a suggested move. And there are two popular rules. One is called metropolis sampling, and the other one is called Gibbs sampling. Now, when it comes to this type of calculations, Gibbs sampling is normally the preferred one, because that introduces the conditional probability and makes it easier to actually make the sampling. So there is a technical issue which we also need to mention today. And then probably we will not get to the code part. So there are elements of the lectures today, which we will also discuss next week. And that is how we actually implement these restricted Boltzmann machines. So we can actually write for some of them our own codes, and you will find that at the end of the Jupyter notebook for this week. But then typically you would end up using PyTorch or TensorFlow and Keras. And you can find some reading recommendations here. As you can see, the textbook by Goodfellow has a pretty good discussion in chapters 18. And the textbook by Babcock and Ali, there's a link here to the codes in TensorFlow for restricted Boltzmann machines. And there is also in the textbook by Foster, if you go into this chapter here, on the GitHub address, you will find examples written in TensorFlow where they actually replace this energy function in the Boltzmann distribution with a convolutional neural network. And there are several interesting examples on how you can actually use these methods. So today, if you want to be a little bit more, how to say, efficient, and you want to look at the more interesting methods, you can think of the Boltzmann machine as a kind of stepping stones which introduce the basic concepts. And then the more popular methods are actually variational autoencoders and generative adversarial networks, and also methods like diffusion models. And these are the topics which we will cover for the rest of the semester, roughly. That's roughly the plan here. So what I'm going to do now, I'm going to switch over to the whiteboard, because there are some basic elements which I just want to step through so that we can slow down the pace a little bit and you don't have the feeling that I'm just throwing lots of equations at you. Now, one thing which, just to quickly remind you, an essential element in order to be able to actually simulate different suggested stochastic variables is Gibbs sampling and the metropolis sampling. These are essential methods in the sampling. So we need to say something about them. And hopefully you will also see why we choose Gibbs sampling instead of metropolis sampling, because metropolis sampling means that you need to sample the whole probability distribution. The Gibbs sampling, on the other hand, deals only with a conditional probability. And that means that it gives a much more efficient sampling over different suggested states or stochastic variables. Okay, so I'm going to switch over to the whiteboard here. And we're going to go through some of the basic mathematical details. And hopefully that will allow you to get some deeper insight about the basics of these different methods. So let me take away this one. Okay, so the basics of all generative methods. So we are going to shift the focus now from making predictions and fitting a model to actually fit a probability distribution, which we then can use to make new predictions, to generate new events or new images if you want to, etc., etc. So this is much more flexible and much closer to the needs in many different sciences. So if you now think of the basics, I'm going to draw a figure here of all generative methods. So this figure, which you will see now, is a little bit oversimplified, but it has the basic content of the generative methods. So you can now think of this domain here as your data set. So this is your data set. And we have some input data X. So this could be a set of images. It could be the handwritten numbers, or it could be images of horses, and you want to make a probability distribution or a model, which then you can use to generate new images of horses. So these generative methods can be used both for supervised learning, but also for unsupervised learning. And the whole idea now is that you, with a probability distribution, you can both make predictions, you can find correlations among the different variables, but you can also estimate the errors because you can set up a standard deviation. Since you have a probability distribution, you would calculate the variance and then you can find the standard deviation. But you can also discuss things like causality. What is the probability of A given B? And this is something you cannot do with the standard deep learning methods like a neural network or a convolutional neural network. They are used to, there you would fit a function, you get a function which has been fitted to the data, and you use that one to make new predictions, but it doesn't give you a probability distribution unless you labor a little bit more. So you would typically have the data set. Then there is something which we are going to call for another space here, and this mimics what we did with autoencoders. And this is normally called the latent space. But you will also see that this can be called the hidden space. And for Boltzmann machines, these are normally called hidden variables. So in this specific case, we have a set of hidden variables, H, and I'm going to define that. And we are going to define a probability here, which is called P of H. Now, in here, on the other hand, in here, we are going to define a probability of a final probability, which is going to be a P of X as a function of some parameters theta. So we are going to make a probability which depends on parameters which will be optimized. So we are going to set up a new cost function which is going to optimize this probability. So optimizing a probability means to maximize the probability. Nobody wants a probability which is 0. You want to have a model which maximizes probability. So theta are the parameters which we are going to try to find. And from here, so this feeds in here, and this feeds back this probability, and it defines some variable x tilde. So the probability which we want is this quantity here. When we have done the training, this is the ideal. There is a link between the hidden states and the final probability, which we are now going to set up through the different equations from statistics. So you probably have heard of things like the marginal probability, the conditional probability, etc. And these are basic concepts which I wanted to remind you of now. So this is the basics of all the generative models. So there's a final probability we want to have, and these theta are typically the parameters of a generative model. So let's now remind ourselves of some basic axioms from statistics before we move on. And then you will see how we will link these different properties. So we have a probability P of H, which we haven't defined, and we have a final probability P of X, which depends on some parameters. But we haven't said anything about how they link. Now, just as a small digression, if you think back to what we did with autoencoders, we had some input data, and then we reduced the dimensionality into something which we call the latent space. And from the latent space, we actually reconstructed a final output X where we optimized the difference between X and X tilde. And that is something which we call the reconstruction error. That was our loss function, which we optimized with the autoencoders. Now, the whole idea here, if you think of this in an overarching way, is that this latent space, which we are going to set up, is going to represent some effective degrees of freedom, which are expressed through a probability distribution. With those effective degrees of freedom, we can then reconstruct the final probability distribution. So it mimics a lot what we said about autoencoders. And you will see this again when we come to variational autoencoders, when we look at diffusion models, normalizing flows, etc. But what you see here is actually the basic concepts. And in order to appreciate this, we need to remind you of some basic elements from statistics. So let me just bring them up here. And I hope you don't get offended. So what we have, suppose now we have some basic events, some stochastic variables defined by different domains. So we have a domain of events, or stochastic variables. And we can define a domain X, which now contains a discrete set. Basically, everything which we are going to deal with is going to deal with discrete stochastic events. But there is no problem in translating this into continuous variables. But essentially, when we are going to deal with whatever kind of scientific problem on a computer, we will always discretize. So I'm just going to set up the discrete case here. But it's pretty easy to generalize this to a continuous case. And then we could have a new domain, which we simply call for y. And then we have y0, y1, up to some yn minus 1. And now we are setting the domains equal in size, but they don't need to be equal. You could have a different length of these domains. And then to each of these, we have a probability. So we have a P of X, where we have X equal to X of I, like that. we will often write this as just a P of X, okay? Now, in the notation which follows here, I'm going to be a little bit, how to say, sloppy with the subscript X and Y, simply just to save notation. So when you see, even if the symbols may look the same, the probabilities are different. So we have a probability for this stochastic events. So that could be some kind of Gaussians. This could be an exponential distribution which generates those events. But the symbols will be lookalikes, and that simply is because I just want to avoid all this kind of notational clutter here. So this would have some Y or J, and we would typically write this just as a P of Yj, but you will also see this as a P of Y for simplicity. So the different P of X and P of Y are different probabilities, okay? So this is just to simplify a little bit the notation. Then we have an important theorem which says that the union of events, which you may have seen if you took a course in statistics, which is written like P. This is the probability of the union of X and Y, and that is given as the probability of P of X. So I'm just stating these. So when you see P of X and P of Y here in the notation, these are different probabilities, but these P's, they look the same with my handwriting, okay? But just keep in mind that X and Y are different stochastic variables, which can be generated by different probability distributions. So one could be a Gaussian, the other one could be a uniform distribution, etc. Okay? And then this is given by minus P, and that's the excluded space. Now, there's another important rule, which is called the product rule, which is also known as the joint probability. So I'm just stating these elements. So X of U of Y can also be written as, so you would often see it like Px of Y. And this is the same as P X. And now comes a notation here, which means the probability of X given Y. So Y has a specific value, and then there's a probability of finding X given Y having a specific value. And this is multiplied with P of Y. So these are now getting into becoming different probabilities. So, and then we have P of Y given X multiplied with P of X. So this is the famous product rule, which is also known as the joint probability. So you're building up a probability of finding both X and Y, and you can write it in terms of the product rule. So I'm not going to prove this, I'm just going to state them, okay? Now, this joint probability, or the product rule, has a specific expression in case X and Y are independent and identically distributed variable. So if X and Y are what we call IID, so I for independent variables and ID for identically distributed, so that means that all the X's follow the same distribution, all the Y's follow the same distribution, and when you calculate things like the covariance between different variables, that is exactly equal to 0. So if they are independent and identically distributed, then the product rule takes a very simple form. It's just given by the probability of X, and now I'm putting the subscript X here just to indicate that Y and X do not need to have the same probability distribution. Okay? So this is the case when they are independent variables and identically distributed. Then it simplifies just to the product. Now comes a very important property, which we are going to use again and again in all generative methods. So this is the marginal probability. This is something which we then can rewrite, since this P of X, we can now actually sum away or integrate up one of the variables. So this is given by the sum over all the i's, which we now put from 0 to n minus 1 of P of X, where Y is given by this Y of I. So this is the joint probability, which we defined before, or the product of the probabilities. And this is something which we then can write when we have the product rule. We can write this as I equals 0 to n minus 1. And then we have the probability of X given that Y is equal to Yi multiplied with P of Y equal to Yi. And we would typically write this in a more compact way as P of X given Yi multiplied with P of Yi. So originally, your probability contains the variables X and Y, and you could think of this as you driving a car in 2 dimensions, and you have the probability of being in a position X and Y. But then you want to integrate away or sum away one of the degrees of freedom, like the Y direction. So then you have the probability of being in a position X, but where you have summed over all the Y values. That's the marginal probability. And you will see that this becomes important when we are going to define Boltzmann machines and generative methods. Because, and I'm going a little bit back here. So if you look at these relations here, like the product rule, this is going to come up again when we link the latent space or the hidden space with the final space. So we are going to have a probability P of H, which links with the final probability. Now, our probability will also be a function of H, but these are degrees of freedom which we are not interested in. So that means that we are going to integrate them away or sum them away. So this latent space at the end represents degrees of freedom, which we don't want to use when we have the final probability, because the final probability is one which now deals only with one variable, okay? So that's a quantity which we are going to use now when we are going to set up the equations which have to be programmed. So the marginal probability is a central aspect of all these generative methods. Now, another probability which you are going to meet is the conditional probability. Now, the conditional probability, if we now say that if this P of Y is larger than 0, then we can define from the product rule. So this is from the product rule. Then we have that the P of X given Y is the same as the joint probability of X and Y divided by the marginal probability of Y. And that is the same as P of X, Y, divided by this sum over I, and then we have P of Y given X of I multiplied with P X of I. So the conditional probability is obviously a condition on X. This reads like the probability of X given Y. Okay? So that's why you have the name conditional probability. And these are quantities. So the reason why I'm bringing this up is that all these quantities pop up in the calculations of the different generative methods. Now, from this, it's pretty straightforward to derive what's called Bayes' formula. Are you guys familiar with Bayes' formula? Anyone heard? So Bayes' formula plays the same role as Pythagoras in geometry. And if I now insert the product rule for P of X, then you get Bayes' formula. So, or Bayes' theorem, as it's called. Bayes was actually a priest who actually had fun doing statistics back in the 18th century. And it was actually rediscovered, I think, by, so my memory fails me here, but I think it was Laplace who actually re-derived this, one of the famous mathematicians. But Bayes was the one who actually came with this theorem, something like 70, 80 years before. I think it was Laplace, but please correct me. And Bayes' theorem simply says now that this P of X given Y is given, and now we are using the product rule by rewriting the joint probability in terms of the product rule. And then we have P of Y here. And this is something which we can rewrite as a P of Y of X. So this is a conditional probability divided by the denominator here, which plays the role as a normalization factor. So we have P, and then we have Y, and then X equal to X of Y multiplied with P of X of Y. Now, these probabilities have a name, and in order to apply Bayes' theorem, we need to have a model for P of X and a model for the conditional probability. So this is the conditional probability. So I can relate now the probability of finding X given Y in terms of another set of probabilities. So this quantity which you see here, the quantity to the left, this is known to the right, this is called a prior. And if the prior is a uniform probability, which is often the simplest ansatz you can make about a variable, because then you are simply giving the same probability to all the events. So if you have 10 events, it's 1 divided by 10. All of them have the same probability with a uniform distribution. If you have a uniform, if the prior is a uniform distribution, then clearly the only thing you end up doing is to multiply this function here, which is called the likelihood. So this is called the likelihood. And you need to make a model for it. So if your likelihood is a Gaussian and your prior is a uniform distribution, then the final probability, which is this one, which is called the posterior probability, becomes just a Gaussian times a constant. Now, Bayes' theorem or Bayesian statistics has been widely used in statistical analysis. And often when you're dealing with fitting large data set, you have two types of approaches. One, which is called the frequentist approach, where you just take the data set and you try to model a probability based on that. Or you start with an ansatz for a probability distribution. You have an ansatz for this likelihood, and then you can set up a final probability, which simply tells the probability of finding X given Y. Now, you can reverse this relation, which you see here, and simply say that if you want the probability of Y given X, then you will simply have to replace Y with X here and X with Y here. So this relation here, this probability of P of X given Y is something which you can reverse here by simply having Y here and X, but then you need to change all the variables here as well. So Bayesian statistics has been widely used, and you will find topics like Bayesian model averaging, where you can use Bayesian statistic to actually find, for instance, the standard deviation, which reflects the different parameters. So you can actually find an error on the parameters which you're modeling the system with respect to. You can use Bayesian neural networks, where you normally replace the activation function with a probability distribution. This is much heavier to train than just using a sigmoid or tan-H or similar functions, which you typically use in deep learning methods. So deep learning methods, I mean, if you wanted to be a little bit more picky and be more rigorous, you could actually replace the nodes and the activation functions with a probability distribution. But that requires much more training. So that's why it's much easier to actually use a fixed function and then rerun the architecture with new fixed functions. So these are some of the basic principles, okay? I hope people are not offended if I just reminded you of some basic statistics here. But these equations are equations which you are going to see again and again. So let's now look at the energy models. So this is our first encounter with these generative methods. And these are also called Boltzmann machines, also known as Boltzmann machines. So what we are going to have now is a domain of events. So this is the data set which we have, x0, x1, up to some xn minus 1. And then I want a probability distribution. I'm going to assume that all these guys here are independent and identically distributed. That's a basic assumption which I'm going to make. So that means that my probability P of x is something which I can write out. I should have this as an uppercase letter of x of I So just a product of all these x's, and then I have a P of x of I. So this is the usage of the product rule. Now, my probability distributions are going to have some parameters which I want to optimize in order to maximize the probability. So in order to find this probability, so I'm going to set up a model. I'm going to use something which is called the maximum likelihood estimation. So what does that mean? It means that my cost function now is a function of some parameters, theta, which I want to optimize so that I get a maximum probability. So what this means is that I want a set of, so my probability P of x now is going to be replaced by a probability P of x as a function of parameters theta. So theta are the parameters. And these are going to be parameters of something which looks like a neural network or similar quantities. And what I want then is a theta optimal. And this theta optimal is then given by argmax of theta, which now has a dimensionality here. So we can have a p variables theta. So we haven't defined that properly yet. And we are going to optimize this probability distribution, I of p of x of I. This is the quantity we want to optimize. Nobody cares about the zero probability, right? So we want to find parameters theta which maximize our probability. Now, when you see that function, when we are going to do an optimization problem, what it means is that, so this is actually the same as argmax of theta, or element, real numbers, of this function P of x of theta. Now, this is a product. And clearly, when we now take the derivatives, so the optimization part, means that what we need then, so the optimization means simply that we are going to take the gradient with respect to theta of P of X of theta, and we want to drive that to 0, as we've done before, okay? So it's not so much different. The only thing which changes from what you've seen before, where the cost function, like in an autoencoder, was just a reconstruction error, which we wanted to minimize, or the mean squared error, which we wanted to minimize, or a cross entropy, which we wanted to minimize. The thing is now that we want, in the optimization part, we want to maximize the probability, and that means that we have an optimization problem where we need to find the gradient of this quantity, period. So it's pretty close. So the cost function now is the probability. But you see that this problem here is not so nice because we have a product. So when we have a product, we can actually circumvent that problem by redefining another function, which makes life easier. So if you think of the product, what kind of function can make our life easier from a mathematical point of view when we are going to calculate the derivatives here? Any good suggestions? Yeah? The log. So the equivalent statement is the following, which makes life actually much easier. So the equivalent statement is theta optimal equal to argmax of theta of log of P of X as a function of theta. So we know that the log function is a function which, when it's a positive, is a concave function. If you don't like maximization problems, you can turn this into a minimization problem. And this is normally the standard approach, because the log, then if you put a minus sign, it becomes a convex function. So alternatively, or theta optimal is a minimization now, argmin of theta of minus log of P of X of theta. So that means that we're going to take the gradients of the log of the probabilities. Because you see now that since you have a product here, you have assumed that these are independent and identically distributed variables. That means that we are going to take the log of these quantities, and that means that we get a sum of the logs of the individual probabilities. And that makes life a little bit simpler. It's still going to be complicated, but it makes life a little bit simpler. Okay? So the other thing now is that before we move on and look at the final equations we have to program, we need to introduce the latent space. So we need to introduce the latent space. And this space is the one which hopefully then, and you will see that when we come to variational autoencoders after Boltzmann machines, it actually is supposed to represent some kind of effective degrees of freedom, like we did in the case of autoencoders. So we introduce a latent space, or hidden space, as it's called in Boltzmann machines, or hidden So with that, we have now a set of hidden events, which are given by H0, H1, up to some H of M minus 1. So the length of that set of stochastic events, so these are also stochastic variables, which are also assumed to be given by an independent and identically distributed distribution. So that means that our P of X now, which previously was defined in terms of X and theta, is going to be replaced by P of X of H and theta. So this is our probability distribution. However, we want the marginal probability. So the exact mathematical relation then of P of X of theta is actually given by a sum over all the HI's element in this domain over hidden variables of P of X of H of I of theta. So the H's are then additional variables, which you can think of in the optimization process in the same way as you've been using a neural network where you have hidden layers, which then give you much more expressivity when it comes to represent a given function or a given set of data. Okay, so this is again the marginal probability, which we actually introduced in here from just the basic statistics concepts. So it's the same object. And you will see that we actually, depending on how we define these functions, we're actually going to get different expressions for the marginal probabilities. Okay, so this is the first step. And what we end up with now is an optimization problem where we now need to define a function. So what we are going to do now is to, when we look at these energy models, we are now going to define this probability of P of Xi of Hj of theta. And we are now going to define, this is a probability, the total probability. So this is the joint probability of the domain X and the domain H. So this joint probability is something which we now represent by a given function, which we haven't defined yet. And Xi, Hj, and then theta. So theta are the parameters divided by a quantity which I'm going to call for Z, which is a normalization constant. If you've taken a course in statistical physics, this has a name, and it's just called the partition function. Okay? So this function, which you see here, is called a normalization constant. And for the physics aficionados, this is normally called a partition function. I know that at least 3 of you are physicists, and you've probably seen some of these elements. So who else has seen this kind of elements in a course in thermal physics or statistical physics? So you can just think of this Z as a normalization factor. Now, this Z then is a factor which now depends only on the parameters theta, which we need to optimize. And you see now that when we are going to calculate the gradients, this Z is going to cause the main problems. So the Z here is actually given by a sum over all the Xi's and all the Hj's. And this is given by F of Xi, comma Hj, and theta. So this is a definition of this normalization constant. Now, just to give you an example, if these X and H's are pretty large spaces, you see that you have to run over actually quite many degrees of freedom. So let's just look at a very simple example before we take a break, okay? Now, as a small reminder, for those of you who have taken a course in statistical physics or thermal physics, you may have encountered the Boltzmann distribution. And that's why these functions are called energy models. So in that case, you have a probability which depends on a given state, a given energy of the system, at a given inverse temperature beta. So this is the probability of finding the system at a given energy in a state I at an inverse temperature. And this probability distribution is given by E times beta of EI divided by Z of beta, where the Z of beta in this specific case is just the sum over all the states E of I of E minus beta E of I. So that's the Boltzmann distribution, which has really described many, many systems in physics. It's been extremely successful in describing phase transitions in physical systems, etc., etc. But you see the parallel here. So we are going to make a model which looks like this, except that now this function which you see here is replaced by this function f, which we have here. But we still have to suffer this factor here, which can become almost impossible to calculate. And you will see that after the break, the kind of equations which we end up with when we are going to calculate the gradients. So our cost function is this one, and we want to maximize it or minimize it. Okay? And the problem is that this function here, the normalization constant, can be almost impossible to calculate. So this sounds really like mission impossible. The other thing, even if you have a nice expression for this model here, it can actually be very cumbersome to calculate directly with respect to all the variables, because you can have spaces which are huge dimensionalities. And you will see that after the break when we look at a simple model. So let me just give you the simple model first, because that leads to a Boltzmann machine, which is called a binary Boltzmann machine. So let's do that before we take a small break. So the example which I wanted to set up before we take a small break is called a binary Boltzmann machine. And we are going to call this a restricted Boltzmann machine. So I'm going to use the acronym RBM, R for restricted and BM for Boltzmann machine. And in that case, in the binary, we are going to assume that X and H can only take two values, so binary from that. And Hj is equal to 0 and 1. We are then going to define a function for f of x. So our f of x of h and theta now is going to be given by e of minus x of h of theta. So this is the so-called energy. And with a binary model, we are going to make a model for this e of x of h of theta, which is going to be given by a sum over all the input variables x and x of I, a of I, plus a new one, j equals 0, up to m. These are the number of hidden variables of bj, plus a sum over ij, and this goes up to m minus 1 and n minus 1 of xi, wij, and b and h, sorry, not b, but h, hj. So these parameters which you see, these quantities which you see now, so these are called biases. And after the break, we are going to see how we can depict this in terms of a graph. And these are called the weights. And the parameters theta are then going to be given by the set of A, B, and a matrix W. So these are going to be the parameters of our model, which we want to calculate the derivatives with respect to. So we are going to train a model where we have defined a probability distribution, which looks like the kind of energy functions which some of you may have seen when you took a course in statistical physics. So is anyone here familiar with something called the Ising model or the Heisenberg spin model? So in those cases, these variables, x and h, would be the spin variables. And this w would be the coupling constant, which expresses the strength of the coupling between the two spins which interact. So in the statistical physics domain, if you were to take a course in statistical physics, you would encounter the Ising model, and that has an energy function which looks like this. It's similar to that. For us, these are going to be the x's, are going to be the input variables, and the h's are going to be the hidden variables. And that will define a network where the weights are playing the same role as the weights you have from a neural network, and the a's and b's are going to be the biases which you have in a neural network. And these become the parameters we are going to train and calculate the derivatives of the cost function, which is the probability distribution. And then we want to drive these derivatives to zero. See, this is a basic overarching picture. And this function E here, the way we have put it up, is actually the simplest possible one. It's a binary machine. It takes values 0 and 1. But we could replace this function here, and this is what many people are doing now when they use Boltzmann machine. You could actually replace that with a convolutional neural network or standard neural network, and then use that in the parameterization of a specific data set in order to generate the probability distribution, which you see here. So this is our final objective, this quantity. So after the break, we are going to set up how we can calculate the gradients with respect to theta of this object. Okay? I hope you see the overarching framework here of what we need to do. And it's a model for the probability distribution, which we have put in here. So you're setting up a model which is going to be trained to reproduce the data which you have. Okay? So I went a little bit over time, but I wanted to have you with me on this. And then after the break, we're going to set up the equations which we need to program in order to calculate the gradients. And with the gradients, we can start doing the training as before. Okay? So let's take a small break here. Sorry for going a little bit over time, but I actually wanted to let's see now. So before the break, I introduced this very simple model. And if we now take a closer look at it, and we now set up a given dimensionality for m and n, then we can quickly see that the dimensionality of the system quickly blows up. So let's just look at the simple case where we now look at a case where we take, so let me just fix that one. So suppose now that this m is equal to 2 here, and n is equal to 2. In that case, the variables x can take the following configurations. 0, 0. We can get 0, 1. We can obviously have 1, 0. And finally, we have 1, 1. Remember now that with x given by a binary set of values, 0 and 1, these are the combinations which we can have. If we now have 2 input variables. So the way you can look at this now is as a network where we have x0 and x1. And if we then take n equal to 2, we would then have h0 and h1. And these are going to be connected like that. And these are the weights. So we would have here the weights W11. This would be the weight W01. This is the weight W10. And this is W00. Now, a Boltzmann machine, so you see this looks like a neural network. You can stack these. You can actually have more hidden layers. But the problem with the Boltzmann machines, these so-called stacked Boltzmann machines, is that they become much more difficult to train. So the standard Boltzmann machine, which you will encounter in the literature and in many, many implementations, is something which is called a restricted Boltzmann machine, where you only have connections between the visible layer or the input layer. So this is often called the visible layer. And this is called the hidden layer or the latent layer. And you see now that the parameters which we need to train in this specific case are 4 weights. So that means that this W is a matrix, which is a 4x4, now 2x2 matrix. And then we have the biases, A0 and A1, and B0 and B1. So these would be the additional parameters which we have here. So we would have a B0 connected with that one, and a B1. And then we would have an A0 and A1. So in total, in this case, we would have 8 parameters, which we need to calculate the derivatives with respect to. Now, you see also that X and H, if I add H here, they will have the same configurations. Now, what this means, if I look at my partition function, so my Z of theta, or normalization constant, as we called it, this is a function over X, all the possible X values of H, and then I have this function F of X, of H, and theta. And in this particular case, this is equal to 2 to the power of 2, which is 4 configurations. And this one has also 4 configurations. So that means that this is a set which represents 16 different summations. So this is something we can do by hand, right? However, if I now increase, let's suppose I increase n for a very modest number, and m as well, to 10, then 2 to the power of 10 is equal to 1024. Then I have a double sum, so I have 1024 to the power of 2, which means that I get 10 to the 6 summations. If I take an equally modest case just with 20 hidden layers and 20 visible nodes, now 20 hidden nodes and 20 visible nodes, then I have 2 to the power of 20, which is then proportional to 10 to the 7th. And then you see quickly that calculating that quantity Z becomes almost impossible, because then you would have 10 to the 7th squared, which is 10 to the 14th evaluations of the function f of x and h. So when I mentioned before the break that the calculation of this quantity, the normalization factor, is actually the difficult one, you see that immediately, even with this kind of small dimensionalities. If you want to use the Boltzmann machine to generate a probability which acts on the MNIST data, then you know that the MNIST data, the full data set, has 28 times 28 pixels. So that means that you would need 28 times 28 input nodes. And that clearly becomes a huge problem if you want to evaluate numerically Z of theta, okay? So I just wanted to highlight the kind of problem which we end up with when we want to use this type of approaches. Okay, so what we want to do now, if we now look at the partition function which we have, so we want this quantity here at the end. This is what we want. If we look back at the data set, or the basic, this kind of schematic image which we made at the very beginning of this lecture. So let's just go back a little bit. So this is the schematic picture. So we want this quantity here. So in order to get that one, we are going to set up an optimization problem. And the optimization problem is now going to be given by us taking the either the argmax over log or the argmin over minus log. So let's just set up the equations which we need to encode. So we are going to have a probability which looks like this: 1 over z of theta time with a product of xi in the domain of x. And then we have this function x of I of theta. And in its full glory, this is now given by the marginal probability. So we have a product over xi's. But then we are going to have a summation over all the hj's because we are going to sum them away. So we have xi, hj, and theta. So we want to optimize. We want the gradient with respect to this quantity of x of theta, and we want to drive that to 0. So our cost function is this function here, and we want to calculate the gradient of the cost function. Now, I wanted to mention another thing here. So you saw from the just a simple model with 2 visible nodes and 2 hidden nodes. Then we had something like 16 variables in total. Then to calculate the probability distribution is something which doesn't require so many floating point operations. However, if you have like the MNIST data set, to calculate just the probability function in a Monte Carlo Markov chain sampling requires incredibly many floating point operations. So if you're going to use the Metropolis algorithm, which is the favorite algorithm in many of these Monte Carlo Markov chain implementations, then this becomes time consuming. And that's why we are going to introduce what's called Gibbs sampling, which then calculates the conditional probabilities. And from the conditional probabilities, reconstructs the full probability. So this is just a kind of small detail, but which actually motivates why one type of sampling is more efficient computationally than the one which is more popular for Monte Carlo samplings, which is the Metropolis sampling or the Metropolis algorithm. But let's now look at the expressions which we need to set up. So what we are going to have to set up when we take the log, this, if we take the log of this probability distribution and look at the gradients, so what we need to calculate is the gradient of, and now I'm just setting up the explicit expression. So I have an x of I, and I need to calculate log f of xi of theta. That's the first term. So what I'm doing now is simply to take the log of this expression, and I translate the product here in terms of a sum. So you see the benefit of actually doing the logs, because then you just replace the products with sums when you're calculating the derivatives. And often these functions here have simple analytical expressions. So if you look at the function we have here, this function is now given, if you take this simple model here, this has an explicit expression given by this simple model. And in the lecture notes in the Jupyter notebook, you will actually find an explicit analytical expressions which you can hard code if you use a binary Boltzmann machine. Now, one thing you will see which becomes a little bit more complicated is that depending on how you define these models, like this is a binary one, you can get simple analytical expressions for the marginal probabilities, the conditional probabilities. But if you want to make your model more complicated, then the derivatives and the conditional and marginal probabilities, all the quantities which will enter the calculations become more complicated. So there's always a price which you have to pay. Here we have a simple model, and obviously a simple model has a limited expressivity. Sorry. Okay, that was a new digression. So let's continue. So this is the first term which we have, and then we have the next term, which obviously has to be minus. And since we have a denominator with z of theta, so we need to calculate the derivative of log of z of theta. Okay? So these are the gradients which we need to evaluate. And if we now look at these expressions, so let's just look at this term first, because that's the one which is going to give complications. If you look at this term, we have a model for f. And since we have a model for f, this is just us calculating for all the xi's which we have. But the term here, since the partition function is a normalization function which runs over all the hidden and visible variables, this becomes much more complicated to calculate. So let's look at how we can actually handle this one. So this is given by, obviously, when we now look at the calculation of the gradient of, or the derivative of the log, is given by the derivative of the partition function and divided by the partition function, which again is the same as this function here. And then I have an x of I. I have my f of x of I of theta divided by z of theta. And this is nothing but the sum over all the xi's. And then I have del of theta of f of xi as a function of theta divided by z of theta. That makes sense? So this is a quantity which we are actually going to express as an expectation value. So let me quickly show you how we can actually rewrite this quantity. So let's remind ourselves that this x of I of theta is something which we can obviously express, and this is a trick, as log of f of x of I of theta. Okay? And that means that when I do that, if I look at the function which we set up on the previous slide, we have a z of theta, which is then equal to a sum of xi of d theta, and then I have the exponential, and then of plain laziness, I'm just going to write just f here, like this, divided by z of theta. Now, this function is nothing but the sum over x of I, and then I have the exponential, and this is a log of f, derivative of log of f, divided by z of theta. And obviously, if you look at this term here, this term is nothing but f of xi of theta. So what I'm having now, if you now also combine the next thing, so if we now take this one, if we take these two together, this is nothing but f of x of I of theta divided by z of theta, which is the same as the probability. So this is the same as p of xi given theta. Okay? That makes sense? That means that I can actually rewrite this equation as an expectation value. So what I have then is the following. I get x of I, which is a sum over all the x's which we have available, p of xi of theta multiplied with delta, the derivative, the gradient of log of f of xi of theta. And this is nothing but an expectation value. So this is the same as an expectation value of this quantity here, delta. And this expectation value is calculated with respect to all the variables in X. So this is nothing but log of F. And now I'm going to skip the subscript X of I. I just write it as a function of X here, of theta. So this is the expression which we need to calculate. So that means that the optimization then of the loss function, which is the probability, that gives us delta theta over P of X of theta. We want that to be 0. That is going to be the same as the gradient of log of F of X of theta minus the expectation value with respect to this domain X of delta log of F. I just write F here without the different variables. So this quantity here, now it depends on whether you want to do the maximization or the minimization. Now we did the maximization. If you do the minimization, the only thing you need to do then is to multiply this expression with a minus sign, and that's it. This is called in the literature the contrastive divergence, but you will also see this labeled as the first term as the positive phase and the other term as the negative phase. Now, the first term is something which we can evaluate directly because we know the different variables which define the function f. However, the second term needs to be evaluated as an expectation value. And this is where the Markov chain Monte Carlo machinery kicks in. So when you look at the expectation value, which we have to evaluate, the only way which you typically can deal with this is in the following way. So let's just put up the expression delta of log of f of x of theta. This quantity here is normally evaluated in terms of a sample over MCS. So this is Monte Carlo Markov chain samples. So you would typically fix a number of samples. It could be 1,000 samples, etc. And this is now given by a sum over I, all the possible events which we have up to this number MCS, which you need to fix. And this is now simply given by the gradient of log of f of x of theta, like this. So this is evaluated by Monte Carlo chain samples. And here we have two basic rules. One is metropolis sampling, which is used to accept one suggested move. Because you're going to propose different values of x of I, and you need to have a rule which either rejects that suggested move or accepts that suggested move. And the other one, which is the one which gives a conditional probability, is called Gibbs sampling. And these are the elements which I want to say a little bit about now. So this is the basic way you would actually solve it. Let's also quickly remind ourselves of the simple binary restricted Boltzmann machine. There are other ways you can do this. There's also something called the Langevin sampling, plus other. So there are several ways by which you can actually do this type of sampling. So the sampling, the Monte Carlo Markov chain is the general algorithm. And within that one, you're going to suggest different stochastic moves. And these moves are accepted or rejected. And there are different algorithms for doing the rejection or acceptance. And the most popular ones in the literature are the Metropolis, Gibbs, and Langevin. and they all are named after famous physicists. The Langevin equation is an equation for stochastic classical motion. Gibbs sampling, Gibbs was a famous physicist, and metropolis as well. Okay, so if we now look at the, if we go back a little bit to this binary BB, restricted Boltzmann machine, then what we defined was a cost function, not a cost function, a function f of e to the minus e of x h of theta. Just let me quickly remind you, because this is a function we are going to use to calculate conditional and marginal probabilities and set up our first Boltzmann machine. So in this specific case, this E is now given by A of T, A transpose times X, these are now vectors, plus B of T times X, plus the vector X times the matrix W times H. And this is the same as a sum over I equals 0 to n minus 1. And then we have A of I, X of I, plus J equals 0 up to m minus 1. And then we have a Bj, Hj, plus Ij, a double sum of n minus 1 up to m minus 1 of xi, wij, and hj here. So we are going to need the gradients. So these gradients of respect to theta, they are going to be given by the gradients with respect to A, the gradients with respect to B, and the gradients with respect to W. So these are the three gradients which we need to evaluate in order to optimize the function. So I'm doing this in a very, how to say, meticulous way, because the basic machinery which you see here is the same machinery which applies to variational autoencoders and also to diffusion models later. So the basic way of the basic thinking. The only difference when we are going to switch to variational autoencoders and diffusion models is that the cost function will change, and also the derivatives, which we are going to look at, will change a little bit. But the basic thing which we have is a probability here, which has a normalization factor, which pops in here. So we need to evaluate an expectation value. And then finally, we have another term here. So these two terms are the terms which can also give us problems numerically, and will be the bottleneck of the optimization problem. Okay? So depending on the type of model which you have, like this binary model, you can end up with simple analytical expressions for the different probabilities and the terms you need to evaluate, or you have to evaluate everything numerically. Okay? Is the, I would say, the big picture clear? Good. So what I want to do now is to very quickly go through the basics of Markov chain Monte Carlo sampling. So how many of you are familiar or have seen the derivations of some of these methods? Okay, so I'm going to give you a pretty rough introduction, because this is at least a double lecture by itself. So I hope I can abuse a little bit on you not having the full, having seen this before. But the important thing is you have to see the basic ideas. So as I said, there are central ways to calculate this expectation value, which we have here. So this is one of the bottlenecks for the Boltzmann machines. And the standard ways of doing that is either to use a metropolis sampling or a Gibbs sampling. And the Gibbs sampling is the one which is the most efficient one, because we actually evaluate the final probability through the conditional probabilities. Okay, so I'm going to switch over to the Jupyter notebook, and we are going to stay with that one for the rest of the lecture. So let's just bring up that one. And you will also find essentially everything which we went through. You will actually find it here in today's lectures. So the material which we've gone through here is actually something which you will see again. Some of these details, you will actually see them again next week as well. But this is essentially where we ended. And you will see now that with this specific function, which we have defined, the binary Boltzmann machine, this is just another way of writing that function, which you have in the notes. You see now that when you calculate derivatives of this specific function, you see quickly that the derivatives of this function e, which we are going to need, are pretty simple to set up. So we have to calculate the derivatives with respect to the weights. So we have a nice model which follows from here. And when we look at the explicit gradient for the different weights, so if we have 2 visible nodes and 2 hidden nodes, there will only be 4 values. If you have 20 nodes, visible ones, and 20 there, you will have a 20 times 20. So you will have 400 values. So this quickly blows up in dimensionality. And the other expressions which you need are actually this ones and this one. So the binary Boltzmann machine leads to actually pretty simple expressions for the derivatives which we have to evaluate. But what comes now is actually a kind of a reminder on Markov chain Monte Carlo. So there are some basic ingredients here which I wanted to say a little bit about. So typically when you study a physical system or systems in the physical sciences, which evolves towards equilibrium from some given conditions, you would start with a probability distribution at some position x, for instance, and at time t0. And you want to understand how the system evolves with time. So you want to reach a situation where after a given number of steps, you obtain a steady state or the most likely state of the system. The problem which we face is that the probability distributions we have are normally multidimensional objects. The analytical calculations are almost impossible, or if they are possible, they are quite difficult. So to sample directly can be pretty difficult, or sometimes even impossible. And also the transition probability to another state is not known. So if we look at the basics of Markov chains, I just wanted to, I'm going to skip some of these things here. But if you look at the Markov process, and you have a probability of jumping, let's say you are in a position j times L, and I times L, so L is a length you jump, then you could say that the probability of jumping from a position I to a position j is given by a half if they are nearby, and 0 else. So this is the probability of making a jump. Now, when you've made such a jump, you can express that with a theory of Markov chains, where you start in a position j at a time t equals 0. And then there is a probability, which is called the transition probability, of jumping from j to I. So this symbol which you see here, j to I, means that you are in this position and you make, this is the probability of being in that position. And this is the probability of making a transition. So this is called the transition probability. The quantity which we want is this one. And it's actually the P's where we have a model for. So we have a model for the Boltzmann distribution, or the energy models as we call them, which is defined by us, like this binary Boltzmann machine. And in that case, that means that the Pj and Pi are known quantities. The quantity which is normally unknown is this W, except for some simple cases which we can make like this. I don't know if you're familiar with it, but this basic equation here, which represents a Markov chain, is intimately linked with the physical process of diffusion. So you can derive the diffusion equation from a Markov chain and vice versa. I don't know if you're familiar with that. So this equation here, that represents a discretized time development of an original PDF with equal probability of jumping left and right. So both of these are probabilities, so they have to be normalized. So pi of t is normalized to 1 at every step. This is normally for discrete processes. It leads to something which is called a stochastic matrix. Now, this W, if you sum all the column elements, they are normalized to 1. Have you encountered stochastic matrices in different courses? So they have some specific properties. They obviously have to obey the rules of normalization. So a stochastic matrix has to be normalized. So if you sum all the elements in a column, they should normalize to 1. So let me give you an example here of a stochastic matrix, because I see that these are things which not everybody is familiar with. So let me just set this up. So the basics of a Markov chain, if we now so we have a probability of being in a state I at a time t, and this is linked with us summing over all the states j which the system can be in at an earlier time, and we have a transition probability of going from j to I multiplied with the probability at a time t minus 1. You can think of this as time. Every time you jump, you reach a new position. So this is our model, our probability model. This is called the transition probability of making a transition from a state I or state j. So this is a transition probability. And this is often for discrete cases. This becomes a matrix. It is a so-called stochastic matrix. So if you haven't met this before, a stochastic matrix is a matrix which has the largest eigenvalue equal to 1. You can actually prove that. Also, the column elements, if you now look at such a matrix, if we now rewrite it in terms of rows and columns, that sums up to 1. So an example could be a 3x3 matrix where W is given by 1/2, 0, 1/2, 1/3, 2/3, 0, 1/3, 1/3, and 1/3. If you calculate the largest eigenvalues of that matrix, so the largest eigenvalue is equal to 1. So you can actually prove that for stochastic matrices. So a stochastic matrix is a matrix which is treated as a probability, in our case, a transition probability. It is normalized so that the columns sum to 1. You can replace that with rows. It's up to you. And it has as a largest eigenvalue 1. This largest eigenvalue equal to 1 plays an important role in the Markov chain, because when the Markov chain converges to the most likely state, that means that the system is independent of time. So if you look at what we had written here, this P, we can actually write this Markov chain in terms of a vector times a matrix. So we could have a vector P at a time t, which is equal to W times P at a time t minus 1. So I'm just stating some of the properties of Markov chains. So when equilibrium has been reached, what happens then is that P of t becomes independent of time. Independent of t. And then we have an equation which just looks like this. So what kind of equation is that? Matrix times a vector is equal to a vector. It has a name in linear algebra. What if I write it in the way many of you may have seen it, A times X? Guess you've seen that one before, right? So what's the eigenvalue here? 1, exactly. So you see now that when equilibrium has been reached, so I'm skipping many of the details, but I just wanted to give you the main message of a Markov chain. So when equilibrium has been reached, you have reached the most likely state, that's what it means, and the system will just fluctuate around the state, and you will be sampling from these stochastic variables around this most likely state, and this is a state which has eigenvalue equal to 1, and this is actually the largest eigenvalue of the stochastic matrix, which represents the transition probability. So this is a system with an eigenvalue 1. Equal 1, which is the largest eigenvalue. Of W. So the most likely state, because typically the system will fluctuate a lot. So think of you, if you look at this system, one very simple example you can think of, if you look at these equations which you have here, this one, which is the mathematical expression for a Markov chain, you could think of you having a cup of coffee. And this P represents the distributions of milk molecules, because you want to have some milk in your coffee. It represents the distribution of milk molecules at time t equal to 0. Then you know that after some time, the milk molecules will diffuse through your coffee. The milk will be concentrated at time t equals 0, where you put in the broth. But after some time, the milk molecule will diffuse in the cup of coffee, and your cup of coffee will look like a cafe latte or whatever, right? And that would be your equilibrium situation. So after some time, you have reached the most likely state, and then all the milk molecules will just be distributed in a uniform way throughout the cup of coffee. That's a typical example you could use in order to interpret what a Markov chain is doing. And a Markov chain is a process which depends only on the previous time, as you can see here. So the Markov chain is the process you use to calculate many of these expectation values in statistics. So when we, next week, when we are going to look at the evaluation of this quantity here, we are going to perform these samples, this sampling, selecting these values using random variables, but we're going to follow the machinery of a Markov chain Monte Carlo sampling. And then when we have selected a point X of I, we need to have a rule for accepting that one and rejecting it. in order to calculate the final expectation value. So next week, we are going to look at Gibbs sampling, and then we are going to set up, so if you go back to the Jupyter notebook, so let me just set up that one because I knew that I wouldn't get time to cover everything this week. So let's just, if we go back quickly to the Jupyter notebook, you will see that after these discussions about Markov processes, there is a discussion of the basic metropolis algorithm, which we will not use, but rather we are going to use what's called Gibbs sampling. So take a look at these notes for next week, because we will discuss Gibbs sampling, which enters actually all these generative models. This is the way we pick the points which enter the calculation of the expectation values. So, yeah, okay, this is an error. This shows that the human who has been writing these slides. So after the Gibbs sampling, what you will find is a long, boring list of how we actually calculate the elements which are needed in the Boltzmann machine. So you will find many of the elements here, and I'm going to discuss that next week. So we have a binary, and that calculates the different probabilities which are needed in the setup of your own program. And at the very end of the Jupyter notebook, and this is also what we will discuss next week, you will find an implementation of a binary restricted Boltzmann machine, where I have coded everything from scratch. And alternatively, there is an example where you use PyTorch. And the data set is extremely simple. It's almost trivial. It's actually us training on the XOR data set. So it's not very advanced, but I will also add examples on how you can use this to train on the MNIST data. So next week, now we have the basics. We are going to look at the actual implementation, and you will see the different code examples which follow the equations in the text here, basically. Okay, we stop here. And for the lab, many of you will probably also like to discuss the second project if you are dealing with two projects. For those of you who have decided for one major project, then clearly we just continue discussing as we've done before. And if you want to grab some coffee or tea, you can go to the CCSE and just get some coffee or tea or whatever you want. Okay.